Okay, so here's the big thing with the zeros. The very first thing we're going to do, we're still going to go through and do the synthetic division. We're going to do some other stuff. We're going to kind of see what's happening with it. But before we do that, let me kind of back up for just a minute and make sure everybody's okay with kind of what we're going for. Is let's say that we had the graph, because this is the part where we're going to tie in the graphs. We're going to put all this stuff together. We're going to tie everything, do all this stuff to make it all kind of work out to be what it needs to be. But let's say we started with something like this. Let's say we had to solve some different things first. And when we're solving this one, because again, solving, we're going to find the zeros. When we graph it, it's the roots, it's the x-intercepts. It's all still that same thing as we're going through these. So it just kind of depends on how they word this one. But what we're going to do is we're going to start with something that is already in factored form so that we can kind of tie it together to see what it is that we have. So let's say that you've got something that's already in factored form and they ask you to solve it. So let's say we had something like this. Let's do x plus 3 times x minus 4 squared equals 0. Okay, so if it's something as simple as just solve, you're going to take each parentheses equal to 0. And solving should be really easy here, right? Subtract 3 from both sides. This one will add 4 to both sides. So there's our two solutions that we have. Okay, now here's where we would tie this in with some of the graphs, and we'll have to add something else in a second. Is that if we were doing this one, let's say we'd gone back and done full method here. If we'd gone back and done full method on this one, this would have been x squared, right? Because we would have done the full method here. If we'd done this thing times x, everybody okay that the leading term here would have been x to the third? If we'd gone back and done the full method on this, that we'd had x squared minus 8x plus 16, and we'd done the full method with that. But anyway, if we'd gone back and put these together, the leading term would have been x to the third. Now, here's where we're going to tie in when we talked about the end behavior a while back. Anybody remember what the end behavior was if that first term was 1x to the third?
It would have been R. So
Mm-hmm.
like this, if it was positive.
Yeah, end behavior, if it was x to the third, that was kind of like slope of a line. Yeah, so it would have been down on this side and up over here. Everybody, that starting to ring some bells, hopefully. We'll let you make the little charts. We had that. So that was kind of what we're doing. Here's how this thing would tie together. And we'll have to bring in something else here in just a minute. Where that all tied together, and this is where we're going to bring in the middle stuff today, is that if we know what these solutions are, you basically go on here and you graph points where those solutions are. Here's one at x equals 4. Here's one at negative 3. Okay, and here's how the end behavior ties in with the graph. Is that on the right side of the graph, we know that everything on the right side is going up. So from the very rightmost 0 that you have, that would be here at 4, we know that this thing is going to go in this direction. And if you go to the leftmost 0 that's on your graph that you have, everything from the leftmost 0 has to go down. And then all we've got to do is we figure out what's happening in the middle and going through these parts. Okay, now the old-fashioned way of figuring out what the graph's going to do in the middle, because the graph could get here, it could go up and do something like this and then come back here, or it could get here and it could turn and do something like this, or we've got all these things of what it's going to do and what it's going to do, which we could plot a million different points in between and find out exactly where everything goes through here to find all these points. But there's actually a shortcut we can do to know whether the graph is going to go this way or do something like this, and we're going to show you how to kind of bring that in so you know what's going to happen in the middle, is that in the middle, where we bring all this other stuff, is that we're going to talk about the multiplicity of the zeros. All right, so the multiplicity of zeros is basically this. The multiplicity is based on the power so the power of each expression or each parentheses in factored form. So we're going to know what this thing is going to do based on when we take this thing and get it factored down to a point. What's that? Based on the power of, that's no up there. Yeah, I got. There we go. Okay, so if it's an odd multiplicity or an odd power, okay, so again, when they're talking multiplicity, we're basically talking about the power. The graph crosses through the x-axis. So if you factor this thing down, we get an odd multiplicity. We know it's going to go through the x-axis. If it's an even multiplicity or an even power, then we know the graph turns around. At the x-axis. So if it's an even power, it turns around. If it's an odd power or an odd multiplicity, then it crosses through. Okay, so we're actually going to go back and show you what this graph would have been on the previous example based on the multiplicity. Once everybody's got everything written down here. Okay, so again, odd power or odd multiplicity, that means it goes through the x-axis at that point. If it's an even multiplicity or an even power, the graph actually turns around at the x-axis, at that zero, at that solution, at that root, whatever they want to call it, for that part of what's going on here. Okay, so if we back up, let me pull the sheet back here to the other part of the page here. So if we back up to the problem we had up here at the top, because basically, again, the graph can either go through the x-axis or it can turn around at the x-axis at that point. If you look at the multiplicity here, the power that would have been here, this would have been a multiplicity of 1. This one, because it was x squared, the multiplicity would be 2. Okay, so when you're going through and checking the zeros and the solutions, this tells you everything that you need to know. Because this was x plus 3 to the first power, at x equals negative 3, this was a odd multiplicity. So 1's an odd number, right? An odd power. So that means this one has to go through the x-axis and do something like this. Which means now we know it doesn't go this way because it has to go to the top. So then we can kind of take this part of the graph out and know that it has to go this way. And then at x equals 4, this was an even multiplicity. So when we were coming down this way, we know once it gets here, it's going to bounce off of this number, and then it's going to head back up this way. And then somewhere in between here, it's going to connect together and do that. Now, what we're going to do is we're not going to worry too much about exactly what this part may look like. I might ask you to find the y-intercept just so we've got another point to reference to know if it's up here at 10 or maybe this is at 2 or something like that, so that you'll have an idea of about how high the graph would go. But I'm not going to worry too much about all these points in between. I'm more worried about, do you know the basic shape of the graph and how this thing's going to go.
How did you get the shape of the graph?
Okay, so that this is, let me think about it this way. Think about if we were graphing this one. If it was x minus 4 squared and we had to graph that one, you okay that it would just be that graph right there? That we would take the graph of x squared and we'd move it 4 spaces to the right side. So that's basically x minus 4 squared here. And then if we graphed x plus 3, that's in y equals mx plus b form, right? So that would be just a straight line that would be going this way. So we're just going to make these two graphs go until they connect each other there. So that's kind of the thought process you want to have when you see like the powers, and that lets you know what the graph is going to do. So if you factor this thing all the way and you get an even multiplicity or an even power, you know that's going to look like x squared. This is like just a regular y equals mx plus b graph, so it's going to be just a straight line part. And we're going to kind of merge those two things together. Okay, so that's how we tie everything together with synthetic division, with all those different things and everything that's happening. The other little thing that may ask you to kind of add in is, you know how when we were graphing x squared, we talked about maximums and minimums. We still get the same thing here, but now they're going to call them relative maximum and a relative minimum, because this is the low point on the graph here, but once we go over here, it keeps on going. So now we're going to talk about not just an absolute maximum, they're going to talk about a relative maximum or a relative minimum. So a relative maximum, that's going to be any peak on the graph. And then same thing for relative minimum, that's any low point on the graph, any trough, any depression, whatever we want to call it there. What's the best word we could say there?
Valley.
Valley? Yeah, we'll say that's a good word there. Any valley on the graph. And again, it's not the absolute lowest point. It just happens to be a low point that's in the graph. So just like if we kind of retrace the graph we had here that looked like this would be a relative maximum, because that is a high point that's on the graph. It's just not the highest point. This one over here, that would have been a relative minimum, because it's not the absolute lowest point on the graph, but it is a low point right there. So it's just a little trough that's there. Okay, so they may talk about just a relative maximum or relative minimum. Again, it's really easy. A relative max is just any peak in the graph. Relative minimum, that's any low point, any valleys in the graph.
So on the graph that we did up on the paper higher,
Yep.
So like the top part would be the maximum and then the floor would be the minimum?
Yes, so you have a relative maximum here, and you have a relative minimum there. And for those, because it's relative, they probably would just have you probably when you graph these, you're probably not going to identify it. They're just, that may be like a separate question where you might identify it somewhere else, because there's just too much other stuff going on. So they probably won't ask you to after you graph this, to then go back and say, all right, tell me where the relative maximum and minimum are. It's just one of those, they just want you to kind of know what it is. So you really won't have to identify those. You want? Okay. So again, I don't think you'll have to really identify these. They just want you to know, any high point, that's a relative maximum. It's not the absolute, it's just a high point that's there. And the same thing for any valley, that's just a relative minimum for what you're looking at. All right, now here's where we're going to tie all this stuff together. We're going to put all these things together. We're going to do as much as we can. We're going to figure some stuff out. Some of these we'll be able to do things fairly easily. Some of these things you might have to go back and do what we were doing in the last section, which was 3.6, to kind of put all this stuff together. All right, so we'll do 2 or 3 examples where we're going to do this. We're going to solve. We're going to state the multiplicity of each root. And again, when we do these, we're not going to make it an absolute perfect graph. We're going to sketch the graph. Now, if we had like 3 hours to do this test, we could actually like graph every single graph and graph every single point and make it perfect. We've got an hour and 20 minutes. So we're not gonna plot every single point and get it so it's exactly perfect graph. We're gonna say, all right, we're gonna get it just a basic sketch of it, so we've got a really good idea of what it's gonna do. Is it gonna be a little off in there? Yeah, probably, but it's enough that we can kind of figure out what's going on with it. So. All right, so let's go x to the 5th plus 4x to the 3rd equals 5x to the 4th minus 2x to the 3rd. All right, so first thing we want to do when we've got the equations is in almost every case you want to get all your terms on one side of the equation just so that it's easier to work with. So let's move this x to the 3rd over here. If everybody's okay, if we'll do this all at one time, we'll also move this x to the 4th over here as well. Because we want this thing equal to 0 so we can figure out exactly what our options are when we try to solve this thing. All right, so we got x to the 5th. We've got an x to the 4th that's by itself. When we move the 2x to the 3rd over, now we've got a couple of terms we can combine. So we've got 4 plus 2. So we can make that 6x to the 3rd. Okay, and once you're here, you've got 2 options. And the first option I would always say is when you get here is, can you factor this thing? Well, they've all got x to the 3rd, x to the 4th, x to the 5th. So let's take out an x to the 3rd and let's see what we've got left over. If we take out x to the 3rd, we're left with x squared minus 5x plus 6. And on the inside, everybody okay that looks factorable? Because if we take away that x to the 3rd for just a minute, if we look at what's on the inside, we're looking for the factors of 6 to equal 5. Hey, that works, right? We can actually factor that. So just be careful with your signs. So what are the factors of positive 6 where sum would equal negative 5? All right, now again, you got to be careful because you could do 1 minus 6 and get negative 5. You also could do negative 2 minus 3 and get negative 5. So again, this is where the signs, you got to be really, really careful with your signs. The b term is negative. So no, the bigger number has to be negative. And if we divide these two, we know then that the other sign has to be a negative also. So it looks like it's going to be negative 2, negative 3. I'll scoot that up just a little bit so we can see it better. All right, so we've got an x to the 3rd on the outside that was the greatest common factor. On the inside, we're able to factor this. And again, it was a nice, easy factor because the inside term started with the x squared term of 1. So that made the factoring a little bit easier. Again, just have to be careful with your signs. Don't fly through the signs because sometimes that'll get you when you go through those. And then from there, it's just setting each parentheses equal to 0. So we're going to set x to the 3rd equal to 0, x minus 2 equal to 0, x minus 3 equal to 0. The solving really easy. Just add 3 to both sides. This one we add 2 to both sides. And this one, well, if it's x to the 3rd equals 0, it's just 0, right? Doesn't matter what power of x it is. If it's x equals 0, it's still just going to be 0. Okay. Now, whether we do this with synthetic division or whether we do it with factoring, when you get to the end, you want to look at the multiplicity of each solution that you have here. So for this one, the multiplicity is 3. This one, the multiplicity is 1. And this one, multiplicity would also be 1. Again, with multiplicity, it's more important to know if it's even or odd. In this case, they are all odd powers, odd multiplicity. Okay, so we've got the solutions. We've got that if we do x equals 0, it's going to be a multiplicity of 3, which means it's an odd multiplicity. If we do x equals 2, the multiplicity is 1. If we do x equals 3, the multiplicity is 1. And then now we got to try to graph this thing. And every graph is going to start off with your leading term. This was x to the 5th, right? So if we do the end behavior, it's a positive number that's x to an odd power. Oh, y'all can't see that, can you? There we go. So when we're doing this, you always go back to the leading term, which in this case was x to the 5th. So if we do x to the 5th, it's a positive 1, x to the 5th power, so it's x to an odd power. So that's like the graph we had earlier. We know the right side is going to go up and the left side is going to go down. And if you didn't have that in your little 3x5 card that we made for the last test, then hopefully you can, always go back for a quick reference on that one because that will help out. All right, and again, how we tie this thing together, how it all goes together, is that we know that these are the 3 solutions that we're looking for. And somebody may be saying, wait, it's x to the 5th. We're looking for 5 solutions. We are, but because this is x to the 3rd, this is x equals 0, x equals 0, x equals 0, because it's going to repeat 3 times. So your power tells you how many times it repeats. So x equals 0 repeats 3 times. So that's kind of where the multiplicity ties in, that we're saying that, all right, the multiplicity is 3. That means we've got to use x is equal 0 3 times. You're like, well, it doesn't matter if we use it 3 times or 175 times. It's still just x equals 0, right? We're only going to graph it 1 time because it's just 1 point, 1 solution that we have. All right, so let's see. All right, so we've got a solution at x equals 0. We've got a solution at x equals 2. And we've got a solution at x equals 3. Okay, and going back to end behavior. Right side's up, left side's down. So from the very rightmost 0, we're going up. And from the very leftmost 0, we're going down. Okay, and again, here's where we're just going to sketch it. We're not going to plot every single point to know exactly what it's going to do. The only thing we know is that all these multiplicities are odd. So every time we get close to 0, we're not going to turn around. We're going to go on through it, and we're going to loop up and do something like this. And eventually it's going to come back, and this one's going through, and this one's going to go through. And eventually they're going to meet and come back together. So we're going to have something kind of like that. All right, and again, exactly how tall this graph is, I'm not really concerned about that. Same thing here. I'm not exactly concerned I'm not overly concerned with where the relative max and the relative minimum are. I just want you to know that if we do this thing, there's a relative max somewhere here, and there's a relative minimum somewhere there. Where exactly it is, I'm not too concerned about it. Again, if we had 2 hours to take the test, yes, we would find out exactly where that maximum and minimum points are, but we've got 1 hour and 20 minutes if we go from bell to bell. So with only a short amount of time, we're just going to make sure that you've got a maximum and a minimum in the right place. And that's all I'm worried about. Okay. Everybody all right there?
Yeah.
Somewhat? Okay. Question? Okay, and then for sure one more. We'll see how much time we have after that. All right, so let's say we've got x to the third minus 5x squared plus 2x plus 8. Okay, first thing is, can we do factor by grouping here? Or would it help any to do factor by grouping? Probably not, right? Because if we do factor by grouping here, if you group the first two terms together, just to show you what would happen, you'd have x squared you can take out. That would leave you with x minus 5. The back two, you can only take out a 2. That's going to leave you with x plus 4. These two things are not the same. So factor by grouping is out. It's not going to work, and it's not going to do anything. So if factor by grouping doesn't work, what do we have to do then? Now we're gonna check our P's and our Q's, right? Yeah. So if factor by grouping doesn't work, we have to do guess and check with long division or synthetic division. So in this case, that means we got to find all the possible factors. We're going to find all the possible, again, rational factors or roots. Sorry, if I can time here. So we're going to do the P over Q thing like we did the other day. All right, so in this case, our P value was positive 8. Our Q value in this case is good because it's just 1. So if we do the factors of 8, it's 1 times 8, and it's 2 times 4. And again, the great news in this case is if the Q value, which would be here, is 1, that makes life a little bit easier because when you divide all this stuff by 1, it doesn't change anything. So we know the only possible real rational roots we have are 1, 2, 4, and 8, some positive or negative form there. All right, again, if this winds up being a group test or a partner test on Thursday, this is where you would talk to your partner and you say, all right, I'm going to check positive 1, you check negative 1. Okay, so here's what I want y'all to do. Y'all go ahead and check positive 1. We're working together. So everybody over here, y'all check positive 1. I'm going to check negative 1, and we're going to see if it's going to work. So y'all do positive 1, do synthetic division with positive 1. I'm going to do synthetic division with negative 1, and we're going to see what's going to work or not. Okay, so did positive 1 work? No, because we get positive 6 at the end, right? Okay, and if you were checking it, there's what the numbers should have been. So now, again, you're going to look to me, you're going to say, hey, did negative 1 work? And I'm going to say, yes, negative 1 worked, because we're going to do negative 1 times 1, which is going to be negative 1. Negative 5 minus 1 is negative 6. Negative 1 times negative 6 is a positive 6. That's a positive 8. Negative 1 times 8 is a negative 8. That is 0. And that is what we want. Woohoo, woohoo, woohoo. So, woohoo. Okay, so now we know one solution. We know that x equals negative 1 is the one solution. And now here's the options. You can either keep doing synthetic division with 1, the negative 6, and the positive 8, and then we'll just go through and we'll check 2s, and we'll check 4, and we'll check 8. But again, anytime you get a solution, see if that thing will factor with what's left over. This started off with x to the third, So this thing is really x squared minus 6x plus 8. Does that look factorable? Are there any factors of 8 that could add up to be 6? Could be, right? 4 and 2 might work, right? So let's just check it and see. Because we got the factors of 8. And we want the sum to equal -6. If 4 and 2 work, we're in business. If 4 and 2 don't work, we're not in business. We got to just make sure the signs are good. It's a -6, so we know the negative has to go with the 4. If we divide a positive and negative, that's also going to work to get us a -2. -2, -4 does have to be -6. We get that one. So those two work. So we don't have to keep doing synthetic division and guessing and checking, because now we know that x minus 2 and x minus 4 will work. And again, those are easy solutions because we're just going to change the signs. So now we got x equals 2 and x equals 4. And there's our 3 solutions that we're looking for. All right, now, once you got your solutions, you need to kind of go back to the beginning and see, okay, which way the graph's going to go. What are you going to do here? It's x to the third, and so far, everything x to the third has kind of followed this same pattern. If it's x to the third, one side's up, one side's down, it's positive, so the right side should be going up, left side should be going down. All right, so when we graph this thing, we need -1, 2, and 4. So there's -1, there's 2, there's 4. Okay, they're all multiplicity of 1, correct? Because when we factored this one, there was only one x minus 2, there was only one x minus 4. This one technically would have been, x plus 1 equal to 0. But again, it only showed up, the answer only showed up one time, so each one of those only had a multiplicity of 1. And again, we had that same end behavior. The right side is going up, the left side is going down. Question?
How'd you get the
So that when we were factoring this part of it off here, the factors of 8 that would equal -6 were -2 and -4. Okay, and then we just set both of those parentheses equal to 0 to get our 2 solutions. So we didn't have to do synthetic division because this thing factored. Now, if this didn't factor, then we'd just go back and keep working synthetic division. Okay, and again, they're all multiplicity of 1, which means once we get one solution and we start plotting these points, once we've got the general direction, we know this thing is going to go through this part. We know this is going through, and eventually, once it goes through, it's got to turn and head back to this one. And same thing here. Once it gets here, it's going to keep on going through, and eventually it's going to turn and do something like that. And that's why you have to know that end behavior, because once you know the end behavior, that sets everything else in motion to get all the stuff that's in the middle. And that's what we're talking about way back when. That's where we're tying all this together.